Hi everybody, hi, Mike here. Today we're going to continue talking about electrochemistry. A little bit of Mike trivia. My degree in graduate school is in electrochemistry. So I kind of wanted to whet your appetite last time by talking about redox, sort of a review from Gen Chem 1. So I'm going to start with one of the examples that we talked about last time, this redox reaction with zinc and silver. And I kind of just gave you the outcome of it. We didn't tell you why we know. Today we're going to find out why we know that this reaction works. There's our oxidation, right? There's our reduction. If you split it into half reactions, which we already did last time, you'll find out, where the reduction is gain of electrons reduction, loss of electrons oxidation. Leo, the lion, goes grr. Now, what we're going to do is talk about how we're going to apply this towards a concept we call a galvanic cell. A galvanic cell is a fancy name. There's plenty of fancy names in science, but especially electrochemistry. And what really bothers me, but I can't fix for you, is when there's multiple kind of definitions or terms of the. So you might hear this called a voltaic cell. It's basically a battery. So let's take that same exact reaction, except what we're going to do now is we are going to connect two separate compartments. In one of the compartments we have zinc in contact with zinc 2+. Now, I'm just trying to simplify here. You know that ain't zinc 2+ by itself. That's got to be something like zinc nitrate, zinc sulfate. But the real action will be not in the other ion, but in the positive ion. So zinc in contact with zinc 2+, silver, because we spare no expense here, in contact with silver ion. Now what happens if I connect these by a wire? That reaction above will proceed, and it'll just trade electrons through the wire. Well, where is it going to occur? Now, if you split this into half reactions once again, it really stands to help you. All right, so I could say, let's split this into half reactions like we did last time. Zinc, I'll leave the solid off, okay? Zinc 2+ plus 2 electrons. All right, and then 2 silver plus 2 electrons going to make 2 silvers. So this compartment here is consuming electrons. This compartment here is producing electrons, and so electrons are going to flow that way. All right? And if we connect them by a voltmeter, we can measure a voltage, which we'll talk about later, 1.6 volts. Now let's talk a little bit about it now. What is a volt? A volt is a measure of potential driving force. So you got a separation of charges, and electrons are going to flow, and the voltage is kind of the energy whereby they will flow. All right? Sometimes it's called potential. Sometimes it's called electromotive force. But what's going on here is we have some terminology that's battery terminology. This compartment, or any other compartment where the oxidation is occurring, is called the anode. All right? The compartment where the reduction is occurring is called the cathode. Now I got a real simple memory trick for you. You folks are experts at what's reduction and what's oxidation. Cathode is where the reduction happens. Anode is where the oxidation happens. The two vowels go with each other, and the two consonants go with each other. So oxidation is always occurring at the anode, and reduction is always occurring at the cathode. That'll help keep you straight. All right, now let's let this rest. Where's the 1.6 volts come from? We're going to tackle that next. But I'm leaving out one very large detail, and that is this battery will come to a halt if you don't have something else present. The reason is that compartment's getting more positive as two zincs. This electrode's actually dissolving. All right, you see? Zinc is becoming zinc 2+ aqueous. That'll actually dissolve, and it's supposed to. This electrode's actually having silver deposited on it, and actually two silvers. So what's going on is this compartment's becoming more positive, and this compartment's becoming more negative, and there could be like nitrates or sulfates. They're going nowhere. And that defies a law, or a pattern, excuse me, in science called the Law of Electro Neutrality, which means every positive's got to have a negative. And so this battery won't really work well unless you have something called a salt bridge. So every battery that touches your life has electrolyte in it of some form. So like your car battery's got sulfuric acid, all right? Your cell phone battery, I'm sure, has got electrolyte in it. So what's going on is, let's just make it simple and make these sodiums. You'd want to make the salt bridge, the salt in it, to be something very inert. You know, you wouldn't want to use chlorides because that might make chlorine gas. So you use something like nitrate. Let's even make two of them because this is a 2-electron transfer. To relieve this electrode becoming more negative than it should, and this electrode becoming more positive, salt ions will flow each way. This is becoming more positive, so anions have got to flow into the anode, all right? And cations have to flow into the cathode. And you see, now don't try to play any memory games. Just, if you can recreate all this in your mind, you'll bulletproof your learning to the point where you won't get things backwards, because in electrochemistry, that's the danger. Getting something backwards is really going to, get you mixed up. So now, that's the components of every battery. The only thing that really changes are what the participants are. So let's talk about how we figure out the 1.56 volts, as well as which way the reaction was going to occur. Let's do that next. Okay, now to proceed, we need to consult with a chart, as I alluded last time, of something called reduction potential. Actually, they're called, because the little E0 is the symbol. You know, that little 0 means standard conditions. So standard reduction potential. Now, you never really have to actually know this, but I want you to have a kind of deep understanding of reduction potential, so you're not just throwing numbers together without some sort of, foundation. This would be if I made a battery, a cell. I'm not going to call it a galvanic cell for a reason. It depends on what the stuff is. If I made a battery of silver versus what we call the standard hydrogen electrode. All right? So if the other compartment that wasn't silver, standard hydrogen electrode. And that is actually a very cumbersome electrode that would be made of acid, H+ ion, 1 mole per liter of that, and then 1 atmosphere of hydrogen. And if you paired it with that same compartment we were talking about in the last battery, the electrons would flow from the hydrogen to the silver, and you'd get a voltage or a potential of 0.8 volts. Now, what if you did that with zinc? If you paired zinc with hydrogen, then the hydrogen would actually take the electrons, and the zinc would actually produce, and you'd get a negative 0.76 volts. So the voltage would flow a different way with each substance. Now, this is what I want you to understand. The reason batteries work is you pair something very electropositive with something very electronegative, and nature will make the electrons flow that way. So for example, if you take cheap batteries, they usually have a zinc anode, and that's because zinc is very electropositive. Then that means its reduction potential is very negative. Zinc is an electron giver. It's a very giving metal in terms of its electrons. Silver, and one of the reasons silver doesn't really react much or oxidize that much, is very electronegative. And so what happens is when you pair electronegative substance with electropositive substance, you get a very, very large potential flowing, all right? And so that's what most batteries are made of. You talk about a lithium battery. Lithium's very electropositive. Zinc is very electropositive. And silver, you know, they make batteries out of silver too, is very electronegative. So how do we figure out what the voltage of a battery is going to be? There are ways to do it. Now, one of the ways you can do this, and I don't like it, but I'm going to show you the way that you might see in a book. It'll say E cell equals, all right, E0 cathode minus E0 anode. I don't like to show that way. You know why? When you subtract something, you got to remember what to subtract from what. Here you actually got to do the mental work of knowing what's the cathode and what's the anode, so you've done all the thinking already anyway. So basically what I like to show is that there's no battery that can be two reductions. This is two reductions. You can't make a battery out of that. So I like to think of it like the one that's more negative on the chart is going to end up being the anode. That's the oxidation. So we're going to turn that one around. So I like to just invert the one that is more negative on the chart. Now I say more negative. That doesn't mean that one has to be negative. Both these numbers can be negative or positive, but there's going to be a difference. So let's write this again. And let's turn around only the zinc. Okay, so I'm going to take the more electronegative substance and I'm going to leave it that way. And the E0 is going to be positive 0.80 volts. I'm going to invert this one. All right, and because I turned this around just like a delta H or whatever thermodynamic property, that inverts the sign. And now you can add these together and there's your 1.56 volts, ladies and gentlemen. And what else happens is we've balanced our reaction because the electrons canceled. And so I'll add these together. By the way, just because I have 2 moles of silver, it didn't change the E0. So whatever, if you got to multiply by a coefficient, that doesn't actually change E0s. They're intensive properties that are due to what the substance is and not how much. So we have this reaction has an E0 value of positive 1.56 volts. All right, now that proves that this is the direction that the battery reaction will happen, and also it tells you that it is a spontaneous or reaction product favored process. So if E0 positive, sorry, my E got jacked up. E0 is positive, that is spontaneous. Or what the newer kind of way is not to call it spontaneous, but to call it product favored. All right? But if you flip that reaction around, that's telling you that that's not the reaction that occurs naturally. That's not the battery reaction. That is the way it goes. If I flip this around, it'd be negative 1.56, and that would be the direction the battery does not go. Okay, I got some homework for you, then we're going to talk about it next time. All right. All right, this is your homework, folks. I've got copper metal in contact with copper 2+. I made it 1.0 molar, so these all match the chart. That's standard conditions. And I got a piece of magnesium, an electrode of magnesium, in contact with magnesium, sulfate, nitrate, whatever. And we're going to connect these by a wire. I'm not going to connect it. I'm going to let you connect it, okay? Like, yeah, I'm not ready to talk about it yet. All right, and by the way, whenever you connect two wires, like I learned in graduate school, put one of your hands in your pocket so you don't shock yourself. But look, when those connect, that wire connects. Ooh, almost forgot my salt bridge. Na plus NO3 minus. Who's going to be the anode? Who's going to be the cathode? Where's the reduction and oxidation going to occur? Which way does the ions in the salt bridge flow? And what is E0? So I want you to figure all that out for me. And if you get stuck, we will be doing that next time in part 3 of our series on electrochemistry and galvanic cells. All right, guys, doing good. Hang in there. Take care of yourself. And scene.